Hey, so today we are finally admitting that air resistance exists. For the entire first trimester of the year, we have said, oh, it doesn't exist. Oh, we're not going to worry about it. Oh, it's not there. But really, it is here, and we're gonna actually look at it today. We're going to try and understand a little bit more about it and how it works. So the first thing that I want you to understand, because we've talked about different kinds of forces, right? We talked about like the force of the earth pulling down. We've talked about like a normal force pushing up. We've talked about other different forces. Air resistance is fundamentally just another version of friction, okay? So I just want you to know that's all it is. It's just a version of friction. So I'm going to write that down here, okay? It's friction as an object moves through the what?
Air.
Yeah. So air is a fluid, right? It's a gas. So if you've ever tried to, like you're in a swimming pool, like let's say a swimming pool is like up to your chest or your belly button, and then you try and run through it, is it easier or harder to run through the water than it would be to run through the air? What's the right answer, Thomas?
Harder.
It is harder, right? Why is it harder? Because the molecules of the water are pushing back on you as you're trying to push forward, right? Same thing is true when you run through the air. It's just that the air is much less dense, so it's much easier to move through. You're also very used to it, right? We've been running through the air forever. That's just what we're used to, okay? But all of those little molecules, as things fall, are pushed on by air. So when I drop the frog and he falls down, we say that he falls down with an acceleration of 9.8 meters per second squared, right? We say that, we know that that's true, but there are little particles of air pushing up on him all the time as he's falling down. So if we had very, very precise measurement tools and we measured the acceleration due to gravity of the frog as he fell down, we would find that the acceleration was not quite 9.8, right? Would it be higher or lower than 9.8?
Lower.
I hear some people saying lower and then some people mumbling, and I'm not sure where we're at. Higher or lower? Why do you say lower? I heard lower. Who said lower? Go either way. Why do you say lower?
Because there's something pushing in the opposite direction.
Yeah, so the net force is going to be still downward, but it's downward a little bit less, right? Absolutely. So frogs are interesting to watch with that, but it's hard to see them slow down because of air. But with you guys know what this is? It's a coffee filter. Yeah, it's just a little lightweight piece of paper. It's like tissue paper, okay, that is nice. And so the nice thing about this is that when I drop it, well, it's kind of fun, right? What's going to happen? Who's going to hit the ground first? The frog. So actually, whoa, like by a lot, right? By an absolute lot, absolutely. So that's really kind of interesting. So they fall down. Why does the frog hit the ground faster? Because he what? Has more mass. Is able to cut through that air much more quickly or much more easily than the coffee filter. But, question, go.
So if you distribute it differently though,
that will affect it as well. Yep, it's the mass. It's also the distribution of mass. And it has to do with a couple of other pieces too. It has to do with how fast it's going, how far it's dropping, and things like that as well. So there are a lot of pieces, which is part of the reason that we don't usually talk about air resistance, because there's just a lot to it, okay? Today, what we're going to do is try and investigate. So here's your question. How does mass affect the terminal velocity? So we need to find out what terminal velocity is. Have you ever heard the word terminal velocity? What's that? So it has to do, yeah, it's kind of like between an initial and final. There's a little bit more to it than that. Does anybody know? You heard of it? Or you have a sense of what it is? I'm going to have you watch. It's a little bit rocky. So I want you to watch this fall and see if you can observe what happens to it. So its velocity when I let go is what? 0. So now let's watch what happens. What happens so from here to here, what happens to its speed? It was getting faster and faster and faster and faster. But then what happened on like kind of the second half of its fall? Did you notice?
Same.
It kind of stuck at the same speed. That same speed, that maximum speed that it hit is terminal velocity. That's that maximum speed that an object is going to have when it's got air resistance pushing against it. Okay, and this definition is it's not complete, but it's good enough for what we're doing. Okay, so that's what our game is going to be, our goal is going to be. Before we actually do that, though, I want to just make sure that we're all on the same page, that we understand the situation here. So I want us to first go back to first trimester, go back to our happy place where we don't have any air resistance, right? In a vacuum, what does a vacuum mean? Nothing. It means that there's no air, nothing in that space, right? Yeah. A vacuum means that there is no air. And as a result, there will be no air resistance, right? This is terrible. In a vacuum, or a place with no air, what does the free body diagram of the coffee filter look like? What forces are acting on the coffee filter? When I let it go, just after it's been released. Gravity, right? This is not a trick question. You've been doing this for many, many days, many, many weeks. The earth is pulling down on it, right? Is there anything else pulling or pushing on it right after it's been released or as it's falling besides gravity? Can you write an F-net equation to represent that? I'm going to try that again. You answer the question this time. Can you write an F-net equation to represent that? That's the wrong answer. Try that again, Jacob. Yes, that's what you really meant, right? I think. Let's try. I'll help you. F-net. It's been, 3 days? You got this, though. F-net means write all the forces that are acting. What's one of the forces acting? Gravity. Fg. Is that one pulling down or up? Down. How do I mark that? Negative. F-net also equals what times what? Mass times acceleration. Hey, which way is it accelerating? Down or up? Down. So I'm also going to write that this is negative because that acceleration is negative. Okay? That is the F-net equation. So now you are able to do that. So that means that when you do this one and I ask you if you can write the F-net equation, you're going to say, yes. All right, awesome. So now down here I can determine the acceleration of my coffee filter as it falls down, 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 right? I know that Fg is equal to mg, isn't it? Always and forever. So negative mg is equal to negative ma. Hey, can you solve that for A? Kaylee says, yeah. What's it going to be? G, right? Like, shouldn't be a big surprise. Divide by m, or divide by negative m. That would be really, really thorough. Acceleration is just equal to the acceleration due to gravity. Not a surprise. This is something that we've talked about for a lot of weeks together. Okay, we haven't written it out like this, but this is the idea. I would like for you to draw a free body diagram for the filter with air resistance. Go ahead and do that. Talk to your table mates if you'd like. Or draw it and compare with your table mates after. Once you've got your arrows drawn, check with your table mates, see if they agree. Why not?
Talking to myself.
I'm so confused. All right.
Yeah.
Josie, did you have one force drawn at least?
Yes.
What was one of the forces you had drawn?
The one that went down.
And what is that one labeled?
Force of Earth.
And then you had what in parentheses? Okay. All right. And then, let's see. Amanda, what else did you have written down? And did you put anything in parentheses for that one? No, did anybody put anything in parentheses for that one? What'd you put, Sam?
No, I didn't say that.
Kaylee, what did you say that agrees with Sam?
Well, I don't know. I just said
FF? That's fine. I would also be fine with like FA for air resistance or SR for air resistance or something. It doesn't matter. That's not one of those we have like a specific thing for. So it's all good. But something else so that you don't have to write air in the bottom here, right? It's all good. All right. Now, question for you. I have a question. Ooh, pick me. Thank you. How should the length of this arrow compare to the length of this arrow? Shorter? Do you agree? Why? Okay, so it still goes down, so gravity's greater. Do you agree? Yeah? Now I want you to watch it again. I'm going to climb up here one more time for you. Okay, here we go. So I want you to watch this carefully. And I want you to think about that air resistance. Watch what's happening. So tell me what's going on right now and then right now. What was happening in the beginning? It was going down. How was its speed? Was its speed constant or was its speed changing? It was changing. So tell me about the net force on it. Was it 0 or no? No. It was not 0. What about at the bottom?
0.
The net force was 0, right? If the net force was 0, what does that mean about the acceleration?
0.
It's 0. And what does that mean about the length of the arrows?
The same.
They would be equal. Are you with me there? So it depends on what part of the story you're talking about. So that's weird. At the top, the arrow is shorter, like you guys said. But at the bottom, once it hits that, what was that word? It starts with a T? Terminal velocity. Once it hits that terminal velocity, then the arrow at the top and the arrow at the bottom are the same length. Because the acceleration is 0, right? Is that making sense? We're kind of putting this all together. This is like putting everything together today. It's a beautiful thing. So I'm just going to put a little asterisk here and say the length changes depending on, what does it depend on? What do you think? Well, the acceleration is a result of the net force. Any idea what the length of or the strength of that force would depend on? Yeah, it has to do with how close it is to terminal velocity. So I'm just going to say depending on the velocity. Yeah. All right, we have a really lovely free body diagram. Given that really lovely free body diagram, Jacob, can we write an F-net equation? Poke him. The answer is? What, Alec? Is the answer yes or no? Can we do it?
Can I?
Yes. Can you?
Sure.
I'm just asking yes or no question. Can you? Could you? Okay, help me out. F-net. Add them up. What do we got?
Negative FG
Okay.
plus the force of the air.
The force of the air, so you can call that FA or FF or F whatever you want to call it, as long as whatever's here is the same as what's up here, right? Those have got to match. And that equals what? Because we're writing an F-net equation. MA. Which way is it accelerating? Down or not at all, depending on where we're at in the story, right? But we'll go ahead and acknowledge the acceleration as being downward, at least at the beginning. So we can write this down again. So this is going to be the same as we had before, except we've got this FF force. So we got mg plus FF equals negative ma. If I wanted to solve that for acceleration, I need to divide by that mass, or that negative mass. Okay. So we can say, I'm going to write this over here, that acceleration is equal to g. It's going to end up being a minus the force of friction over the mass. If the force of friction it gets really, really like as big as that, then this is going to go, then this part's going to kind of cancel out so that this is the same size. If the force of friction is as big as the gravitational force, this would be mg, then this goes to 0. If it's not as big, then we've got acceleration downward. Okay. But either way, the acceleration here is going to be less than the acceleration here was. Does that make sense? Our goal today is to figure out how the mass, and we're going to quantify mass in terms of the number of coffee filters. How does mass affect the terminal velocity? Because it's going to have a different terminal velocity depending on its mass. That's what we're going to do today. So I'm going to show you how to set this up in just a sec so you can kind of see what's going on, and then we'll collect data. We're going to collect some data today. We'll do the rest of it tomorrow. If you don't get all the way done, it'll be all good. You spent some time with the little lab quest last trimester, a few weeks ago. This little guy right here. Does this look familiar to you? We did this when we did our friction lab. We had the little force sensor that we plugged in here. Okay, so this little guy is going to have a USB that's up into your Chromebook. Okay, and this one also is going to connect to the sensor that we're going to use today. So this sensor here is called a motion detector. It uses sonar, okay, in order to measure distance. Have you ever heard the term sonar before? Where have you heard of sonar before?
Subs.
Subs? Submarines use sonar? Absolutely they do. What's that? Tesla currents, is that what you said?
Cars.
Oh, cars, yes. They use sonar for, I don't know what they use sonar for. For what?
Lane detection.
Oh, yeah. Okay, gotcha. Yes. Same deal, right? They use it to be able to tell where things are relative to them. Are there some animals that use sonar? Bats do, absolutely. Dolphins. So people are excited about that. Okay. So all of these things, whether it's self-driving cars, whether it's bats, whether it's dolphins, whether it's whatever, the way it works is that it sends out sound waves, and those sound waves go out and they hit something, and then they bounce back. It's just an echo. And then the computer, or the computer in the car, or the brain of the animal calculates from that how far away something is and how fast it's moving. It's pretty amazing, okay? So you're going to use this little device here. It'll plug in, and then it'll start making really obnoxious little clicking sounds, okay? So you may need to unplug it in between if it's driving you nuts. I'm just letting you know, okay? But when you hit collect, then you can actually measure, it'll measure the distance that something is as a function of time, okay? So taking a look up here at the technical procedure, you're going to connect the motion detector in the lab quest to the Chromebook and open up graphical analysis. If you do not have graphical analysis on your Chromebook yet, you can just do a Google search for graphical analysis and download the Chrome app. That's all you need to do. You're going to stand up high. So that would be on a lab table, that would be on a desk, that would be somewhere high, because you need some space for your coffee filter to fall and hit terminal velocity. Because if it doesn't hit terminal velocity, we can't take any data. Okay? You're going to drop it, you're going to hold it like this. You're going to place the coffee filter here, about 50 centimeters underneath there, and then you're going to let it go. click to begin collecting data before you drop it. Okay, you want to make sure you do that, otherwise it's not going to work very well. So you have one person holding this and holding this, the other person's going to hit collect, you'll hear the clicking, and then you'll drop it and let it fall, okay? Make sure when you do that, some people like do like this and then leave your hand here, and then it's just measuring where your hand is. That doesn't do you any good because you actually want to see the thing fall, okay? If the motion looks too erratic on the graph, then repeat it. Make sure that it makes good, make sure it looks nice before you move on, okay? I'm going to let you get set up and get started and try and take some data. I'm going to walk you through the graphical analysis part after you have some data to look at. One thing that I do want to make a point of when I was making this last night, I didn't do a very good, thoughtful job about the data collection graph. I gave you a little space to write data, but it is not very good. So I want you to add some lines. Okay, so that you've got multiple trials. Okay, you'll need some good labels and all that sort of thing, but I'll let you guys do that part. All right. Okay.